Thank you, Nate. Good morning. My name is Lorenzo, and myself and Antonin here are kicking off the working group today. I will be spending a few minutes describing what is the goal of the working group and the charter of the working group, and Antonin will discuss some initial work that we have been doing on API. P4 defines a pipeline, forwarding pipeline, and this pipeline needs to be managed. I mean, it needs to be managed runtime. For example, you need to instantiate flows in tables. It clearly is desirable to do this in a standard way so that we create some portability, we create some independence from hardware vendors, either switch vendors or silicon vendors. And that's all the working group is about. Here, we are showing two pieces of code. There is a snippet of P4 code that just instantiated a simple LPM table, and there are flow match action that you will want to instantiate in this table, and all this working group is about is to define a standard way to do this, which takes me to the next slide. We will think that we want to define two flavors of API. One is a local API, and the purpose of the local API is to allow programs that run directly in the switch, applications that run directly in the switch, to control the P4 pipeline and to manage the P4 pipeline. This provides SDK independence and silicon vendor independence. We also want to define a remote API, for example, an RPC API, with the intent of being able to manage full switches that a vendor might give you, and also this provides independence from a switch vendor. As I stated earlier, the main intent is runtime management of P4 tables. However, this also extends to managing externs and also being extensible to manage vendor-defined externs. Finally, for the remote API, at least, we will want to define some minimal session management so that this is completely implementable API and can be actually used. Which brings me to one more thing, which is configuration. If you want to manage a switch, beside runtime management of the dynamic state in the table, you also need to configure the switch. Here we are not proposing to reinvent a new way to configure switch, but there is definitely some time that is needed between a P4 runtime and configuration entities. For example, P4 runtime reference ports, and those ports needs to be managed. So what we will want to do here, what we are proposing to do here is to use OpenConfig and define a YANG schema that is P4 friendly. And in fact, here we are proposing to reuse as much as possible existing schemas and just add whatever it's missing to make this work. This brings me to the next part, which is Antonin.
Hi. So I just want to say a few words about some initial work we've been doing on one possible runtime API, which we call P4 runtime. So this is one possible runtime API for P4 programs that meets the goals that Lorenzo has been describing in the previous slides. So this P4 runtime API is a result of a joint effort between Google and Barefoot. It's still ongoing, but we are open sourcing all the work we've been doing as soon as we do it. So this API is targeted at SDN deployment with a remote controller, which is why we've been implementing it using protobuf and gRPC. So protobuf because we needed a serialization format for the flow messages that we send to the switch, and gRPC because it integrates well with protobuf, because we needed an RPC mechanism, and because it has a lot of nice features like bidirectional channels. So my first bullet point here is that this API is protocol independent. So if you've been using P4 for a while and you've been building control planes for P4, you may be familiar with the C PD API that we've been using, PD standing for program dependent. So this is an auto-generated C API based on your P4 program. For this API, we decided to go with a protocol-independent API. So the API itself doesn't change when you update your P4 program. Only the data that this API is going to carry between the controller and the switch is going to change. And we did it to facilitate vendor adoption, because this way a switch vendor just has to implement this API once, providing the API can support multiple P4 specifications, and to enable field reconfigurability. So if I update my P4 program and I recompile my P4 program, I can push the compilation output to the switch using the P4 runtime API, and I don't need to recompile any code which is running on the switch. So this API has been developed like specifically to control P4 forwarding plane. So all the constructs that you can find in P4.16, you will find them expressed in this API. So of course, table and table programming, that's a first-class citizen in P4 runtime. We also support all the PSA, portable switch architecture externs, because we believe that to make the API usable, we have to embed support for those externs. Otherwise, you can just control tables. But because we also want like all vendors to be able to control their vendor-specific externs using this API, we support extending this API for arbitrary externs. So if you have a new extern, you just have to come up with a new protobuf message description for your extern, and all the data you need to control your extern can then be carried over this gRPC interface. However, as Ned said, we don't require the target to be fully P4 programmable for you to use this API. For the sake of portability, for the sake of being able to control hybrid deployments with fixed function devices and P4 programmable devices, well, we want you to be able to use this API. So providing your fixed function, let's say chip, as a forwarding behavior, which can be expressed with a P4 specification, even though this is a single P4 specification, you will be able to use this API. Finally, in addition to the goals that Lorenzo was describing previously, this P4 runtime API supports like packet in, packet out, using a gRPC bidirectional stream. It also includes support for master-slave arbitration if you want to replicate your controller. However, the master election process is out of scope. How you choose your master is up to the controller. And finally, we also support batching in the RPC definition. So you can, with a single RPC message, perform multiple updates across multiple P4 components of various types. And in the slides, which will be uploaded, I included a link to our initial work. So this is a protobuf and gRPC definition for P4 runtime. To piggyback on Lorenzo's example, so here I reproduced the P4 table definition expressed in P4.16. You have one logical view of a flow that you want to program into your table, and to the right you can see what the protobuf message looks like. So this is completely independent of the P4 program. The format is not the data. You see that we chose to use IDs in the P4 runtime API to keep the messages small. Those IDs are allocated by the P4 compiler, and the P4 compiler also produces a mapping between names and IDs. So this workshop is the occasion for us to launch the P4 API working group, so the third working group for p4.org. We have written a charter document with Lorenzo, and we will be uploading it online shortly. We'll also write a blog post on p4.org to detail the scope of the working group. I'm including the mailing list for the working group here. At least at first, all the work we'll be contributing will be included in this repository here, so you can also create issues and start discussions on this GitHub repository. And we welcome new ideas and contributions. If you're interested in participating, you can send us an email, and if there is sufficient interest, we may even have teleconference meetings on a bi-weekly basis, for example. Thank you.